All right. This is 4-1. Just one lesson. I did not split it up into multiple days. There's a few slides here, but really just one topic. And the topic is sampling. Okay? Overall, in Chapter 4, what we're getting into is how we put together experiments. Okay? Eventually, we want to get to the point where we can make some conclusions from the studies that we look at and put together. Okay? If we want to make meaningful conclusions, our studies or experiments have to be set up properly. Okay? And this is kind of laying out a really common thing in statistics, actually like a fundamental thing, is that typically the data that we choose to analyze did not come from the entire population. Rather, we take a small little subgroup that we call a sample. Here's our sample. It's always our preference. It's much more realistic. A lot of times looking at the whole population or gathering data on the whole population is time-consuming, expensive, and in many situations just not even possible to do, let alone do it accurately. So we tend to operate off of samples. This whole lesson is about how we pick them. Okay? Because if we want to rely off of analyzing a sample, which you can, right? Well, you could, during election season, you could take, even if it was a nationwide election, you could gauge what percent of people are going to vote for a candidate within about 3%, 3 percentage points of margin for error from polling about 1,000 people, okay, in a country that has 330 million, okay? Less than that in terms of registered voters, but it's pretty staggering the amount of accuracy you can have from a sample if it's taken correctly, okay? In this first one, population, think of who the sample was drawn from. It's all the students at the school. The sample is the 100 who were surveyed. So what they would like to do in that situation is make a conclusion about all the students at the school. It doesn't say what size it is. I'm assuming well over 100 students, just from talking to 100, or getting data from 100. Population on the second one would be the cans produced that hour. This problem does make a reference that the 10 cans for the sample were selected in a given hour. And really, when you think about the population, you should kind of take the approach that, are we talking about we like to just call them individuals. In the first problem, it's a student. In the second problem, it's a can. Is it possible that they were picked? So from what it's describing in the second one, if the can wasn't produced that hour, it's not even possible that it was picked. So I did say for the population, it's all the cans produced that hour. And then the sample would be the 10 cans selected. All right, so the rest of this lesson is kind of about how do we go about putting together good samples. Sometimes a contrast is nice. Let's actually kind of flip the script and talk about how to do it badly. which is good to be aware of. You see this happen all the time. This is a really, really broad term. I wouldn't say it's like a sampling method, because you'll see in this lesson you have 3 that you should know. A convenient sample is just a really broad term. It basically means violating all the rules that we want to adhere to just to get the easiest sample possible. Okay? This is a term to get to know. When that happens, it almost always inevitably systematically favors certain outcomes. That's what bias is. It takes some outcome of whatever data you're gathering and makes it more likely than it really should happen. Okay? That's what bias is all about. And if you just, don't pay attention to the principles of sampling in this lesson and you want to get data fast and easy, you probably have bias that you're dealing with. This is a bad sample, right? Sometimes it happens. Sometimes you have to do it. We should avoid it. It's really common. You could say it falls under the umbrella of a convenient sample, but to take a voluntary response, which is where in a study you let individuals in the population choose if they want to be in the sample. It's a bad idea. Okay? If you can avoid it, don't do it. Almost always results in bias just because it's more likely that people that have a strong opinion about whatever is, they chose to participate in the study or they chose to offer information, and they probably have their reasons that they feel strongly one way about it or another. Okay? We don't want that. It means they may be more likely to offer a certain response. Take a minute and read through the context here. Certainly pause if you need to. Okay. The question on this is now a few years old. Arizona doesn't have this law anymore, but it still illustrates the concept well. Was the city council right to pass a boycott of Arizona? And the results showed 96% of the 41,000 in the sample said no. Okay? Does this result represent the opinions of all Los Angeles residents? First of all, the answer would be no, it doesn't. Okay? I would say those with the opinion of no may be upset and more likely to answer. %. Is likely too high. That is typically what you get with voluntary response bias. Okay? Here, those that disagree are probably going to be more vocal about it than those who agree. Okay? They probably make up an abnormal proportion of the 41,000 who responded and gave us a statistic. That's what the 96% is. That's a statistic. Okay? A percentage that was gathered from a sample, and is probably higher than what it actually is. This would have bias. Allowing people to choose themselves gave basically a systematic way for us to get the answer of no at too high of a rate. All right, convenient sampling is bad. Voluntary responses are bad. Randomness is good. Okay? That is the type of, that we've basically moved on now, that we're now talking about good sampling, right? Random sampling. So typically you specify whatever sample size you want. Larger samples are more accurate because they have less margin for error. But whatever sample size you chose, every single possible sample that you could get of, let's say n is 25. You're going to select a sample of 25. Every possible sample of 25 has to have the same likelihood of being picked. It's got to have the same likelihood of being picked. Okay? We don't want people to kind of exercise their opinion if they want to participate. We mathematically want a system where everyone is equally likely to get selected. That creates really good samples that are a lot like the population. Table of random digits is not a thing. There is a random number generator on your TI 83 or 84 calculator. I will show you how to use it if you need it for a homework assignment. Table of random digits is also in the back of the book. We don't use it. All right, so here is, if you were kind of to explain a method as to how we would do this, okay, and it might be a little bit funky. You can kind of go one of two ways. You can use a response that's called hat theory. That's what I typically do. Or you could say a random number generator. Okay? We have 21 stores. We want a random sample of 3. Here's how we describe it. Before I do this, remember that the name of the response I'm going to give is called hat theory. The key word being theory. It illustrates randomness, but it's theoretical. We don't actually go do this. In reality, the randomness would be done with a random number generator. Okay? Write all 21 stores on separate pieces of paper. Put them in a great big hat. And then randomly select one. Write it down. Put it back. That's a little bit of a weird thing to do, but we'll talk more about that in class. Write it down, put it back, and repeat until you have 3 unique stores. These 3 stores are your sample. Okay? With that description, every single possible sample size of 3 had the same likelihood of being picked. That's good. That's what a simple random sample is all about. This hat theory description basically went through what we would call an SRS, or a simple random sample. Okay? One big hat, all the stores in the hat, randomly take one out, write it down, put it back, and do it again until we have 3 of them. And then we've got our sample. Okay? All right. There are 2 other good sampling types that you should know. Simple is the one you just saw. That's a really important one. There's also stratifying. Okay, I'm going to kind of throw all these together in one big example here in a minute, because on the next 2 slides I'm going to show you 2 of them. Okay, basically, if you have little subgroups that are kind of they have like characteristics, and you want to take a little SRS of each of those subgroups, and then you're going to combine the two, or three, but we take separate random samples from each of the strata. That's what we call a stratified random sample. Okay? If you had a study where you wanted 50% of your participants to be male and female, instead of taking one big SRS, you could stratify off of gender and say I'm going to do an SRS of females and I'm going to pick 30, and then I'm going to do an SRS of males and I'm going to pick 30, and then I know I'm going to have the 50-50 ratio that I wanted. That's kind of what stratifying is all about. A cluster sample is very different. Okay? You still divide it up into smaller groups, but these smaller groups are way different. Not only do they have no like characteristic, they're like little mini populations. Okay? So when we pick a cluster, we would still do it randomly, but if we do that, we're taking every single individual from the cluster. This is the only sampling technique that we do where you can make one selection and you will take multiple individuals, because when you select the cluster, you take everybody in it. Okay? You take everybody in it. Now, hang on a minute with this slide. It's a little bit of madness. Okay? It's got the three parts because I chose one context here, which if you need to stop and read it, it's a little bit wordy, but when you get through all of it, it's not that bad. Okay? But it's got the three parts because I'm showing you the three different sampling types. Okay? So here's basically the deal that this paragraph is taking you through. You have two towers, north and south. Okay? The one to the north is newer. Each of the towers have standard rooms, and they have 2 floors of suites. Half the rooms face the beach, half the rooms face the street. Okay? Those little characteristics that I'm identifying, those are reminding me of strata, right? And I might need to stratify this problem. But for part A, let's say we don't. Okay, so you may want to put a note in here. Part A is just describing an SRS. Because if you add up all the rooms between the two towers, each one has 400 rooms, and 40 suites. Okay? So a total of 880. A simple random sample would say, give each room a unique number from 1 to 880. Use a random number generator. Select 88 unique random integers. And then the rooms that correspond to those numbers, that's your sample. Okay? That's a simple random sample. Everybody, if we had done the hat theory, everybody is together in one hat. Okay? Now, that may not be the best way to go because we had all these differences. Remember? The North Tower is newer. Some of the rooms face the beach. Some face the street. Some are standard rooms. Some are suites. Okay? I don't want to hear from 88 rooms that are all in the North Tower. Or to hear way more from rooms instead of suites. I don't want to hear from everybody that had a view facing the street. Okay? I want to hear from all these. Okay? So this problem is stratifying. So in each one of these I went through, and notice, each offers a slightly different case. Look at the first one. South rooms, beach. This would be like its own hat right here. I would do an SRS with those 200 rooms. South, rooms. Let's get 20 that face the street. Their responses might be different, but now I know I've got them. I've got South Tower rooms that are facing the street. North, room, beach. North, room, street. Okay? Now there's half of them. What's left? Okay? Suites, right? After those 4 strata, we haven't heard from anybody that's in a suite. Not good. We want to hear from them. Okay? Now there's a lot less of them, and notice with these numbers I'm sticking at selecting 10% because we had said before that as a total we want to take 88 of the 880. So now I'm just taking 2. South suite faces the beach. South suite street. North suite beach. North suite street. When that whole process is done, put everybody back together, and you have a sample of 88, but now every single possible room type is included. We're going to hear from everybody we want to the extent that we want to. Last one. This talks about a cluster. Okay, the 2 towers had 24 total floors. Okay, I think each tower had 12. Okay. A cluster sample would be to say randomly select 2 of the 24 floors. Okay? With a cluster sample, when you select that floor, whether it's, the suites that have 20 per floor or the rooms that have 40, you're taking every single room on the floor. Okay? That's the difference. Here I would just label the floors, not the rooms. The floors label 1 to 24. And I'll take 2 of them. But if I get a floor of rooms, I'm taking all 40 rooms. If I get a floor of suites, I'm taking all 20. That's where cluster sampling is different. It may not be good. Okay? And here's why. I could get 2 floors that are only in one of the towers. I could get 2 floors from the south. That's not good. I don't hear from anybody or get any data from the north. Okay? What if I only get rooms? What if I only get suites? What if I only get people facing the beach and not the street? Sometimes cluster sampling is a good idea. In this one, not really. In fact, if I were to rate them, I'd say the cluster sampling is the worst. The simple random sample would be second. The stratified, I think, is the best for this context. We love to rely on sampling. Even if it's done well, remember we have margin for error in our results. If done well, larger samples offer less margin of error than smaller ones. Okay? Even without bias, right? If it's accurate, we still again have some variability in our results. The larger the sample, the less that we have.